Hello and welcome to another video. I'm going to work through a step question here. I think it's excellent though. I think a lot of the old step 1 questions, particularly ones which are on certain topics like this one's on sequences, are excellent practice for the MAT if you're doing the MAT in November. The step 1, which no longer runs anymore, I think went up to about 2018. They're dead easy to find the past papers. And obviously have a go at this question first before you watch my solution, because kind of typical to the MAT, it starts off nice and then escalates and gets quite nasty towards the end. And I think it's good for the MAT because it's about sequences, and they often have these recurrence relation sequences tested in the MAT. I've seen them in lots of times. So yeah, this is a good question for that kind of practice. And obviously I'm trying to nudge those people doing extension papers in my school just into doing a step a day as you're going through the the 6 weeks holiday. And it doesn't have to be step, could be MAT, could be older BMO questions. Try and avoid round 2 unless you're super brave. I think round 2 is ridiculous. I can't do them. But yeah, okay, let's have a go at this anyway. So this question, quite like this. And I'll be honest, the reason I'm doing it is because I looked through my old step solutions and I didn't have one for this question. I've had most of them. I had every other one in the pure section for this paper, but I didn't have question 7. So I guessed that I probably found it too difficult at the time, and it never hurts to come back to these. And so that's what I did. Anyway, let's have a look at it. So yeah, this looks like a kind of Fibonacci kind of like sequence, the way it's defined. Next term equals previous term times P plus term previous to that times Q. Okay, well, let's bear that in mind. Now, okay, start off by saying show that if Tn equals x for all values of n. Okay, so that's straight away telling me every single value of n, Tn takes a value of x. In other words, every single term in this sequence takes a value of x. Okay, so this first question is really just testing, do you understand the notation? Yeah, that's really what it is, because it's not that difficult once you realise doesn't matter what n is, because it's for all values of n, Tn equals x. So Tn plus 1 equals x, because just let n equal n plus 1. This is supposed to work for any number you give to n. Yeah, and n is obviously a whole number here. Okay, so bearing that in mind, we can see that x equals px plus qx, because every single term in this sequence is x. And then it's very easy, because x is non-zero, we can safely divide by 0 and get 1 equals p plus q, since x doesn't equal 0. And therefore we've arrived at the result. There we go. That's it. That's part 1 done. And x can be any non-zero real number. Yeah, you can see it holds for any value of x, provided x doesn't equal 0 here. Otherwise, we'd have division by 0 problems. Okay, so that was a nice start. That's what I thought. 2 was a little bit harder. I thought t to the 2n equals x, t to the 2n plus 1 equals y for all values of n. Yeah. So what I guess this is saying is the even terms in the sequence, the even position terms in the sequence are x, and the terms in an odd position in the sequence must be labelled y. And we've got to show that q plus or minus p equals 1 this time. Well, let's say, we can obviously see here that t to the n plus 2 equals p times t to the n plus 1 plus q times t to the n. All well and good. Now, if n is even, yeah, because n might be odd, but if n is even, then, well, Tn would be x, because we're basically saying here any even term in the sequence is x, and then the odd term is y. Now, if the even termed position is x, then this one would be y, and this one would be x again. So we're going to have x equals py plus qx if n is even there, yeah? But on the other hand, this should also work if n is odd, yeah? And if n is odd, then this recurrence relation should also hold, because it is the definition of the sequence. And then we're going to have y equals px plus qy, quite simply because n is odd this time, yeah? Now, these two equations should hold, basically, all the time. Yeah, because if n is even, that should hold, and if n is odd, this should hold. Yeah, so we're going to get two different answers, or two different conditions on Q and P, if you like, from each one of these sequences. Now, the way I'm going to do this is I'm going to solve them simultaneously, because I want to eliminate x and y essentially. So if I rework this first one and have it as x times 1 minus q equals py, and this one I'm going to rearrange into y times by 1 minus q equals px. Then I can easily see that if I eliminate x, what I'm going to have is py over 1 minus q equals y times 1 minus q over px. Over p, sorry, because I'm making x a subject here and x a subject here and equating the two. Okay, the y's straight away cancel, and we're left with, if we times the p's over and times the 1 minus q's over, p squared equals 1 minus q all squared. Yeah, lovely. Because if we square root, then we get p equals 1 minus q, or p could equal a negative of 1 minus q, which is q minus 1. This is a bit like if you've got x squared equals y squared, or shall I use different letters so I'm not confusing these, nothing to do with the question. If you had a squared equals b squared, and you square root, then you can conclude that a equals b, or a equals negative b, because negative b all squared would be positive b squared, etc, etc. You don't have to think about plus or minus on a, because you're just going to end up repeating the same thing basically, and there's only two possibilities: a is b or a is minus b. And so we've got p is 1 minus q, or p is q minus 1, and that means that q plus p equals 1, or if we rearrange this and to add the 1 over, and we can have 1 equals q minus p, and hence q plus or minus p equals 1 as required. Cool. Deduce that either x equals y or x equals minus y unless p and q take certain values which you should identify. Well, this is kind of like mysterious, this last little bit, but when you think, well, this is about division by 0, those values are going to be q is 1 and p is 0. Yeah, straight away you can see, because that's where you're getting the division by 0. It's where at the start, at the start here, if you look at these two equations, if you had q is 1 there, and p is 0, then it doesn't matter what the relationship is between x and y, because you've got 0 equals 0, and that's why these two don't hold when p takes the value of 0 and q takes the value of 1. So anyway, we've got to deduce first that x equals y, x equals minus y. So if we look at the first one, we can say if q plus p equals 1, then obviously p is 1 minus q, and so now if we go back to this stage, x times 1 minus q equals py, but of course p is 1 minus q, so you get xp equals py, and so you get x equals y. And it's not going to come as much of a surprise to note that when you have it the other way round, q minus p equals 1, then you're going to have q, how shall I do this, 1 minus p is 1 minus q, and so using this same equation here, we'll have x times by minus p equals py, and so x equals minus y in this case. Yeah. Note this doesn't hold. Oh, note. If p equals 0 and q equals 1, then these relationships are unnecessary. Need not hold, I'll just put, because the original condition is satisfied anyway if q is 1 and p is 0. Both those equations are satisfied. So unless p take certain values which you to identify, we've done that. Okay, right. Part 3. Now, always think about, what the question's kind of setting you up for. The thing which is different about like STEP and MAT questions compared to Olympiad questions is that they give you hints. They genuinely do. They're trying to hold your hand a bit. They're trying to show you a new trick. Granted, the maths is very difficult, but they want you to succeed, actually. You can see that with the way the question's written. Yeah. Notice in the first part, we solved one equation, essentially, to come up with condition on P and Q. Just one unknown. There was just X involved. In part 2, there's X and Y involved, and we solved simultaneously, essentially. Well, in part 3, we've got X, Y, and Z, and so we're going to solve simultaneously, but we're going to solve a system of 3 equations, which is definitely something you need to be able to do if you're doing any extension papers. But anyway, look at this. We've got t equals 3n, subscript 3n equals x. That's just saying every term in the sequence which happens to fall positional wise on a multiple of 3 is going to be x. Every one which is 1 more than a multiple of 3 is going to be y, and every one which is 2 more than a multiple of 3 is going to be z. Yeah, so we're kind of establishing periodicity with this sequence. That's what we're doing. We're just determining the period, because like if you take the last one, like, that has a period of 2. You know, every 2 terms it's repeating x, y, x, y, x, y, x, y, x, y. That's the whole point. That's what the sequence is actually doing. Well, here we're going x, y, z, x, y, z, x, y, z, x, y, z, which is interesting. Yeah. Okay, right. But let's set it up. So I'm just going to use the t to the n plus 2 equals p times t to the n plus 1 plus q times t to the n. Now, I don't feel like I get this right unless I just done part 2 first, because part 2 is kind of like showing you how it's done. Yeah. If you know, if n is a multiple of 3, what do we get? Well, if n is a multiple of 3, then this is going to tn is going to be x. 1 more than a multiple of 3 is going to be y, and this is going to be z. So we're going to have z equals py plus qx. Like, on the other hand, if n is 1 more than multiple of 3, and I'd rather write these down actually next to each other, so can I just move this over? Yeah? Or I'll put them side by side. If n is 1 more than multiple of 3, we're going to get, everything's going to basically shift along 1, because, like, you know, okay, it's the middle term which is a multiple of 3 this time, which means that this one's going to be 2 more, you know, the next one up, y, and this one's going to be the one which is missing, z. And, you know, if n is 2 more than a multiple of 3, it moves across again. And I hope that makes sense. So we're now going to have x here, and then we're going to have pz plus qy. Just kind of like rotate positions each time, yeah? Now, what are we going to try and do to prove this? Well, you know, our trick seemed to work quite nice for proving that result last time, but this time we've got 3 equations, 3 unknowns. Treat p and q as if they're constants, but we're essentially solving for x, y, and z. So first thing I'm going to do is I'm going to eliminate, I think I eliminated x first, yeah? Let's call these a, b, and c. Yeah, let's use a and b first. And let's note that if I use a, I could easily rearrange that into x by doing z minus py over q. So I've turned that into x being the subject. I'm going to do the same thing here and have y minus qz over p. Now over here, I'm going to use, or just under here, I'm going to use b and c. Yeah, and I'm going to eliminate x again, so I'm going to have y minus qz over p, but that's going to be equal this time to pz plus qy. Cool, so I've got rid of my x's. You know, I'm being nice and systematic here so I don't get too lost. Now I've got 2 equations and 2 unknowns, so I'm going to try and get rid of, you know, another letter basically. Now we'll have to do a bit of rearranging first. So if we call, you know, give them little names, call this one diamond and call this one star. Yeah, so if we try and reorganize diamond first, and I think I will use this pen because it's a bit thicker. Okay, so I'm going to have zp minus p squared y equals yq minus q squared z. And I quite like to rearrange this so I've got this in a nice format, all the z's connected together, all the y's connected together. So I'm going to have that as z times p plus q squared equals y times q plus p squared. Yeah, it's quite tidy now. Do the same thing for star. I'm going to have y minus qz equals p squared z plus pqy. Rearrange to make the z's together and the y's together. Well, we're going to have y times 1 plus, 1 minus pq. Careful with that. It's easy to make sign errors in this. Good news is we know the answer, so they are trying to help you. Like I say, they do help with sign errors and stuff like that by supplying the answer. P squared plus q. Okay, cool. So we've got them in nice formats now, and now we could easily rearrange to make y the subject, for example, or z, depending on what you want to eliminate. I think I actually eliminated the y's next, so I got z p plus q squared over q plus p squared. That doesn't cancel. That's y. Equals, well, what would y be over here? Z times by p squared plus q over 1 minus pq. Now the z's cancel, and I'm now hoping that this turns into this lovely, didn't mean to take that way, this lovely cubic expression, which they said it would. Yeah, that's the trick. Now, okay, right, what we're going to do here, that times that, p plus q squared times by 1 minus pq equals p squared plus q multiplied by q plus p squared. That's the same thing, isn't it? So we're just squaring out a bracket there. Okay, so here, what are we going to get? We're going to get p minus p squared q plus q squared. Try and be systematic when you multiply out these things. Minus p q cubed. And then we're going to have p to the 4 here. That's a bit disturbing because I'm sure it's cubic. Plus 2p squared q plus q squared. Now, the nice thing is the q squareds actually cancel, and then you can divide everything by p. That is nice. Okay, so what are we going to have? 1 minus pq minus q cubed equals p cubed plus 2pq. And lo and behold, we get their answer. P cubed plus q cubed plus 3pq take away 1. Yeah? Okay, so we've proved it. Yeah? Now, I got this far in the question, no problems at all. It was here on the next bit where I started to really scratch my head. Often the case, isn't it? Like when you're doing mat and step questions, it's a bit at the end which gets the better of you. Yeah. I hope I hope you managed to battle it through, but hope you definitely want to be in a position where you can sort of get a good 3/4 of the way through a long mat or step question before you take these exams. Okay, if the bit at the end's still puzzling you, well, that happens, doesn't it? But yeah, okay, here we go. Now, first thing I thought though was, did you say either p plus q equals 1? And I thought back to, because straight away I realised they were doing things about the periodicity of the sequence. Now, this first one, which we did right up here, we also had p plus q equals 1, because this is a situation where you've just got in your sequence x, 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 x every single time, whereas this is describing a situation where it has a periodicity free, i.e. it's going, well, basically z, y, x, z, y, x, z, y, x, because it will start on z, I think, and then it will be, well, actually, will it start on y? Let me just think. Y, z, x, y, z, x, y, z, x, if n is, if n is 0 or 1, depends if you start on n is 0 and is 1, but anyway, point is, this is looping round 3 times, yeah? Surely it includes a situation where x equals y equals z, yeah? In other words, every term is just the same, in which case p plus q equals 1. So this surely corresponds to when p plus q equals 1, where you get, guess what, x equals y equals z. So I thought that bit's kind of obvious to me. Yeah, it's because of part 1. And then this bit I just looked at and thought, you what? That must be the alternative, obviously, when x, y and z are distinct, and in that case x plus y plus z is 0. But I wasn't really too sure, but the way I argued it thus was like this. I said, okay, so as a result of sequences with a period of 3 actually having a period of 1 if everything, actually having a period of 1 if the terms are all the same, if it's actually got a period 1, if x equals y equals z, we have p plus q equals 1. Oh, we have p plus q equals 1 from 1, i.e. p plus q minus 1 is a factor. So that's how I determined that that would be a factor of this. And then I just thought, well, what do I need to multiply it by to make that? Yeah, because I'm hoping it eventually turns into that lovely sum of 3 squares. I can see why they want me to express it like that, as a sum of 3 squares equals 0, because if the sum of 3 squares equals 0, as every term is strictly 0 or bigger, you must have, therefore, p equals q, p equals minus 1, q equals minus 1, and then the question's going to be easy. But yeah, this little bit of division can be quite awkward though, so we're trying to turn it into that. So I thought, well, I need a p squared, because that's going to make a p cubed, and it's going to give me a p squared q, which I don't really want, and a minus p squared, which I also don't really want. And then I thought, well, I need a q cubed as well, so I'll stick in a q squared here, and I get a p q squared, kind of like similar to that one, a q cubed and a minus q squared, so very similar to the one above. And then I thought, well, I want to get rid of some of these things. Well, if I put a p here, that gets rid of the p squared, so I get a p squared, and that gets rid of that. It gives me a pq, and it gives me a minus p. I thought I'll do the same for the q to get rid of the q squared. Now it gives me a pq as well, annoyingly, and I thought, I feel like one step forwards, one step backwards here. I get a q squared, I get a minus q. By the way, this is always the way I do division. I never use long division because it confuses me, so I just do multiplication instead. Okay, right, what do we got to get rid of now? Well, we don't need p's and q's in there, so I really want to get rid of that. So, and also I need or minus 1 on the end, so I thought, well, I'll stick on a 1 here, because if I have a 1, I get a p, I get a q, that cancels those, that's looking good, and I get a minus 1. Now, what have I got and what am I missing? I've got a pq and a pq here, 2 pq, which I kind of want to get rid of. So if I have a minus 2, if I have a minus 2 pq, or minus pq actually, yeah, that would work nicer, minus pq, because that's going to give me a minus p squared q, it's going to give me a minus pq squared. That kind of sorts out the 2 up here I wanted rid of. Then it's also going to give me a plus pq. Yeah? Okay, and then look at that. I've got a pq, a pq, and pq, which is my 3 pq. So I've correctly factorised it. Hence, p cubed plus q cubed plus 3pq minus 1 is actually identical to p plus q minus 1 multiplied by p squared plus q squared plus p plus q plus 1 minus pq. Cool. Okay, that's nice, yeah? And I guess what I need to do now, because that first bracket obviously gives us p plus q equals 1. We'd already determined from the start, as I said, just because of the result in part 1, it just made it obvious to me that x equals y equals z would be the solution where p plus q equals 1. We've already proved that, p plus q equals 1 comes from the fact that when all the values in the sequence are the same, you get the result of p plus q equals 1, i.e. x equals y equals z. Now, hopefully we can turn the other bracket into this, yeah? So let's see if we can, yeah? Okay, right, what have we got here? Well, remember, this equals 0, yeah? So I'll keep writing down this just so I can write the conclusion nice and clearly in the end. What I'm going to do is double both sides of this. So I'm going to turn this into 2p squared plus 2q squared plus 2p plus 2q plus 2 minus 2pq. Yeah. Now you might think, why have I doubled it? Well, firstly, double zero is 0, and secondly, I'm looking where I'm going. Yeah. If you look at this, I want to end up with a p squared plus 2p plus 1. 2p note. I want a q squared plus 2q plus 1. 2q note. So that's why I've got, look at that, I've got a p squared in there. We can rewrite this now as, right, okay, I'll keep a p squared there, and I'll keep a q squared there, but then I've got a p squared plus 2p plus 1, so I've got a p plus 1 squared. Yeah, that's p squared plus 2p plus 1, so I've used up that. Same with a q squared plus 2q plus 1. That turns into that. So I've accounted for that one, and that one now, and now I've just got a minus 2pq on the end. Well, that's lovely, isn't it? Because this now turns into the result which I'm looking for. So I've got p plus q minus 1, and then I've got p minus q all squared. I can now write the second bracket as the sum of 3 squares. And now I can say, hence, p plus q equals 1, or p minus q squared plus p plus 1 squared plus q plus 1 squared equals 0. Yeah. Now, this one, I mean, I think it's just obvious. Didn't we prove that in the first part, that if p plus q equals 1, then, you know, all the values of x will be the same? Like, well, I suppose we need to be a little bit more careful. I might prove that one in a second. I'm going to look at this one first, though, and point out this only holds. Yeah, let's split the page in half. This holds if p equals minus 1, q equals minus 1. Yeah, we need every bracket to be 0 because it's a square. It's always going to be 0 or bigger. So we need that to be 0, that to be 0, and, well, p has got to equal q as well. Well, that's good news because p does equal q. Yeah, well, clearly it does. Great. It holds. Okay, so how am I going to work out the conditions on x, y, and z? I'm just going to use the original equation, you know, z equals py plus qx. As z equals py plus qx, plug it in, you're going to get z equals minus y minus x, so z plus y plus x equals 0. See, I told you that would correspond to that one. Now, I was a bit paranoid here because I wanted to really prove that if p plus q equals 1, you definitely get x equals y equals z. It took me a fair old faff around to do it. It really did, because I was like, well, okay, let's use these equations. Z equals py plus qx. In fact, let me use diamond and star. Let's just do it here, yeah? So, if p plus q equals 1, then looking at diamond, yeah, we're going to have z minus py over q, but q is just 1 minus p, equals y minus 1 minus q is just 1 minus p, isn't it? Yeah, 1 minus p z over p. So I'm just getting rid of the q's there. Okay, now if we multiply this out, we get zp minus p squared y equals y times 1 minus p minus 1 minus p all squared times z. Yeah, took me a while to prove it, like I say. Then I got zp. I probably should have actually, should I might be easier using this version. I'm just going to go backwards a little bit just because I think it's going to be easier if I've already isolated the z's and y's. So if I use this one here, yeah, let's not star it, let's call smiley face. Okay, like using smiley face. Okay, we've got z times by, okay, it's p plus q squared and then q plus p squared. So p plus 1 minus p squared equals y times by 1 minus p plus p squared. Yeah, and if you multiply this out, you get p plus 1 minus 2p plus p squared equals y times 1 minus p plus p squared. And basically you're going to get z equals 1 minus p plus p squared. Look at that, it's identical on the left and the right. Now you might want to be careful because you could be dividing by 0 here, but I think if you've got p squared minus p plus 1. If we just quickly complete the square on that, p minus a half squared minus a quarter plus 1, that's going to be plus 3/4. You can see that's strictly greater than 0, so we can safely conclude that z equals y. So we've shown that z equals y. Now, it'll be exactly the same for showing that y equals x, but I would just argue that these are symmetric equations, yeah? And so they should have identical roots, like, if x equals a as a root and y equals a as a root and z equals a as a root. Well, I've actually got y equals z is what we've proved, and I can just say by symmetry, x equals y, because everything's just shuffled over one. It's going to be exactly the same. And we're going to have x equals y equals z. I wonder though, I couldn't really tell from when I looked up the mark schemes for the old papers for step 1s aren't really mark schemes, they're more like hints, and I couldn't really tell if they were going to definitely give me full marks or some marks for my kind of somewhat hand wavy appeal of, look, it's p plus q equals 1 again. It's going to be the case where all the terms in the sequence are the same. Hopefully I get full marks, but you never know. Okay, so I hope that was useful. Remember what I said in the summer, a step a day. It does help, it really does. They don't take too long, and you can do it. That's the important thing. You can do it, and even if you can't do the whole question, you can initially, when you start, maybe you can do 40%, 50% of it. That's good. Keep going, keep practicing. Just keep trying different questions. You'll see where your strengths lie, and that's good for you. Okay, hope you enjoyed the video. All the best, and bye bye.